In this video, we are going to understand the concept of binary classification, which is a supervised machine learning. Now, when we are dealing with binary classification, our target outcome is to, don't forget, supervised machine learning works with label data. So that means the target variable we are considering for a binary classification is 2. Is either 0 or 1, good or bad, yes or no. So for this particular video, we are going to be making use of a loan approval data set. So let's load in the necessary libraries, then we load in the data. So we'll say import numpy as mp, import pandas as pd. We execute that. Then we load in the data set df equals to pd dot read underscore csv. Then we have the loan data that we are considering. It's the loan data. Then we say df.add to display the first 5 rows of the data to have a view of how the data set looks like. Oh, I didn't put the extension, so don't forget to always add the extension. So we say .csv. Okay, so we see we have the first 5 rows. So these are the columns where structure. You can see the loan status. Maybe the person is approved for a loan is 1, or the person is not approved is what? Is 0. Is what? Is 0. Approved 1, not approved 0. Okay, so the next step is to check maybe there's a missing values in our data. It's good for you to check if there are some missing cells so that you can deal with it before you proceed, so that it won't stop you halfway. So we come over here and say df dot is null dot sum. So as you can see, everything 0, 0, 0, 0, 0, 0, everything is good, no missing value, so we are good to go. So the next step is supposed to be maybe a data visualization or explorative data analysis, but we are considering just machine learning. So we'll go to the next stage. So the next stage is going to be to convert all these categorical columns to numbers. Why? Machine learning models does not understand letters or characters. They understand numbers. So being that, we have to find a way to pre-process all these columns that are categorical in nature and convert their values to numerical value. So what are we going to be using? We are going to be using a function from the module in scikit-learn called label encoder. How does label encoder work? Label encoder encodes each value in a column in ascending order. For instance, if you have A, B, D, E, and rest, it's going to sort it first, then tag each alphabet with a number starting from 0 in ascending order. So after that, it goes to each column. Anywhere you see that particular value, the first value, tag it with 0, like that until it gets to the last word value. So we import that to say from sklearn dot pre-processing import label encoder. So we activate it, we say encoder equals to label encoder. Then let's select all the categorical columns so that we can apply this label encoder on it at once instead of picking the column one after the other. So we say categorical equals to df.select underscore dtypes include columns that are object in nature or category in nature. Then we use the loop to loop through the column. We say for x in categorical. We say df.x df_x equals to encoder dot fit transform. That's same word. So what they are trying to say is go to categorical, pick the column, go back to df, match it together, then use the encoder to transform it. So let's see what we have on our df now. So we say df.add to see the view of our data now. What do we have? We have an error. say, oh, there's a mistake, we made a mistake. This object, we put double E, so let's remove one E. Okay. So look at how the data is looking like now. So we have what? Everything is well set. So we can go ahead with what? With the machine learning. So for classification, either binary and the one we talked about in our next video, which is multi-classification, it is prone to some errors. Number one is class imbalance. What do they mean by class imbalance? This is our target class, which is the known status. If we are requesting or if we survey 1,000 rows of data, it's expecting that 1 is supposed to be 500 and 0 is supposed to be 500. I know it's not possible. It's not possible for, it is on a rare case you go out to collect data and you have equal amount of what target what outcome. So if you finish your machine learning and maybe your accuracy is not okay, that could be one of the problems. And if your accuracy is too high, sometimes maybe 100%, or it's too low, sometimes it could be due to overfitting or underfitting. So let's build our machine learning model and let's see if we encounter any of these problems, maybe overfitting, underfitting, or maybe the class imbalance has power over the outcome of the data. So for this, let's start with let's split our data into independent and dependent variable. So our dependent variable is the lone what? The lone status. So we say x equals to df dot drop lone underscore status. So what are we trying to say? We are trying to say all the values that will be assigned to x, remove lone what status. So that's why we say x equals to 2. You drop out the lone status, then you assign other column to x. So let's have y. Our y is going to be the known status. Our y is going to be the known status. So we are going to split this our data into two parts, which is the next step, training and the testing set. Why? Well, we can't just build a model and deploy it without verifying, without validating it. For instance, before they release an Infinix phone or maybe Techno phone, they didn't validate it. They just released it. They won't get to know, okay, maybe the power button is functioning properly, the screen is functioning properly. So the same thing with our models too. We have to train them. After training them, we can't just deploy them. We have to validate it that, oh, this model is suitable for the task at hand. So we are going to split our data into two sets, the training set and the testing set. So the training set is always more than the testing set. If you have a large data, you use 70-30. But if the data is relatively small, you go with maybe 80-20 or 90-10. Okay, so let's split our data. For this, we are going to be using 80-20. So we say from sklearn dot model underscore selection import train test split. Then we'll say xtrain ytrain xtest and y test equals to train test split. Where are we training? Where are we splitting for? Where from x and y. Now say the test size is 0.2, which is 20%. Then random state, so that we can have equal shuffling. Let's use 42, so that we can have equal shuffling. So for instance, if you use this random state, the way it's going to shuffle the data, because this data, before it can select it, is going to shuffle it. It's not that it's going to select from 1 to 80%, assign it to, no, it's going to randomly shuffle it, so that when the data is going in for the machine learning model to learn, it's going to be able to find all the possible patterns and features and learn properly. Okay, so let's execute that. So our machine learning training data and testing data is ready. So we are going to be using the base algorithm first, which is logistic regression. So for classification, either binary or multi-classification, the base algorithm is what? The linear what? And the logistic regression rather. Okay, so let's import the logistic regression. We say from sklearn dot linear underscore model import logistic regression. Then we activate it. we activate it and we'll say model 1. The reason why I'm putting model 1 is because I'm still going to try out another algorithm. Why? It is good you try out multiple algorithms to know which one is going to be best fit for that particular data set. The logistic regression might not perform better, while some advanced algorithm will perform what? Better. So model 1 equal what? Logistic regression. Okay, so now we should understand that each algorithm has its own parameter. For logistic regression, you can see these are the parameters behind the what? Logistic regression. So if you execute it and you don't have the right outcome, you can come back here and tweak any of those parameters to try it first before you conclude for another algorithm. Try it, tweak any of those parameters to see if the accuracy or the precision or any of the metrics outcome is going to what? Improve. So let's fit in our train data set now. So we say model 1 dot fit x train and y train. So we execute it. So at this point, you can see what we have. We have a warning. It's trying to tell us that total number of iteration reach limit. Basically, the solver that they are using would not convert very well. So let's try to change the solver. Like I say, we can tweak the parameter. So I say solver. Let's try this one that says Newton Koleski, and let's see. Okay, so using this particular solver, it was able to convert very well. So now we are going to evaluate. At this point, the logistic regression is done learning. So it's ready for deployment now, but we can't just deploy it now. We have to validate it. So to validate it, we have to use some metrics, like the precision, how precise is the model in predicting the target variable, the recall, what is the core percentage in telling us that this will be approved or it will not be what? Approved. Then what is the overall accuracy? What is the overall what? Accuracy. Then we check the error margin using the confusion what? Metrics. Check the error using the confusion metrics. Maybe it's a type 1 error, a type 2 error, or a type 3 error. So say from sklearn dot metrics, I'll say import classification report. Classification report in confusion metrics. So we have to predict with the X test. So we say predict 1 equals to model 1 dot fit, or rather dot predict X test. Then we say print classification report of Y test and predict 1. So we use the sharpen to compute the confusion metrics. So we say import sharpen as SNS. Now we say CM to represent the confusion matrix. CM equals confusion matrix of Y test and predict 1. Now we say predict 1. Now we say SNS dot heatmap, SNS dot heatmap, then CM R naught equals true, FMT equals 0.5G. We have to put it in quotes. So let's run it. So you can see we have the outcome. 89 overall accuracy is 89. But you can see for class 0, which is loan that are not approved, and the one that are approved, you see there's a big difference. So that means there's a class imbalance. That means in this our data, we have more of loan that are not approved compared to those that are what? Approved. That's why you can see there's a high margin between the precision of class 0 and precision of class 1, we call like that. But the overall accuracy is what? It's 89. So we have the confusion matrix. This is a type 2 error. This is a type 2 what? We have a type 2 error here. So let's look at it. We use the recall to compute this. You only use the precision maybe when the recall is 100% and there are still some errors here, then you use the precision at that point to compute it. So you can see, how do you know the true outcome? The ones on the diagonal, are the true outcome, meaning they are the true percentage of the record, while the one else surrounding it are the remaining percentage, but they are errors. They are what errors? So this is the true zero, false zero, the true one, and false what? And false one. So let's try out another algorithm to see if it's going to beat the accuracy of logistic regression. So we say from sklearn, let's use the random forest dot assemble import the random forest classifier. So we are going to activate it. We say model 2 equals to random what? Forest classifier. Then we say model 2 dot fit x train and y train. We execute it. It's ready. And if it is ready, we are going to evaluate it. So the random forest will take time because it's a collection of trees. So we have an algorithm called decision tree, while the random forest is a collection of that decision tree. Okay, so the random forest is ready. So the same way we evaluate the logistic regression is the same way we are going to evaluate the random forest classifier. So I copy that part, I put it there, then I say this one is predict 2, model 2, predict 2, predict 2. So let's execute it and let's see what we have. Okay, so you can see this one, the accuracy is more better. We have 93%. And if you see the precision and the F1 score for class 2 is also more what? Better. And you can see that the error margin point as what? As reduced. So it is good. You try out more than one algorithm so that you can decide which one is the best fit for that particular data set. So, but in this case, there is a case of class imbalance, which we are going to talk about in our next video. We see in our next